Okay, welcome to our fourth tutorial. In this tutorial, we're going to talk about the general approach to hypothesis testing. We'll also talk about types of errors that can occur when we are conducting a hypothesis test, and we'll introduce the concept of statistical power. So let's talk about hypothesis testing, also known as tests of significance. So these are the steps for hypothesis testing. You begin with an assumption and clearly state hypotheses. Make sure assumptions for hypothesis testing are met. Calculate a test statistic. Calculate a p-value. And reject or fail to reject the null hypothesis. And so whenever you're asked to do a hypothesis test, so for example, examine differences between groups, you should make sure that you address all of these steps. So the first thing we do is begin with an assumption and clearly state our hypotheses in relation to that assumption. So in today's tutorial, we're going to talk about how to test a hypothesis about the mean of a single population. This isn't really very applicable in real-world research because we're usually interested in comparing differences between groups, for example. But understanding how to conduct a hypothesis test involving the mean of a single population is a good place to start when learning how to conduct a hypothesis test in general. So let's talk a bit more about what this first step means. So to perform a hypothesis test, we begin by proposing a null and alternative hypothesis. Our null hypothesis, designated as HO, is generally a statement of equality. And we always begin by assuming that this is true before performing our hypothesis test. The alternative hypothesis, designated as HA, contradicts the null hypothesis and is usually a statement of difference or change. And this is most often the research question that we're actually interested in. To give an example, let's say we know the true mean blood pressure of the general population, and we're wondering whether the mean blood pressure of coffee drinkers is equal to or different from the true blood pressure of the general population. Our null hypothesis would be that there is no difference in blood pressure of coffee drinkers and the general population. These means are the same. Our alternative hypothesis is that there is a difference in the blood pressure of coffee drinkers compared to the general population. In other words, the mean blood pressure of the subpopulation of coffee drinkers is not the same as the general population. So if we were to conduct a hypothesis test, we begin by assuming that the null hypothesis is true, that the mean of this subpopulation of coffee drinkers is equal to the general population. Usually we hope that our sample data can discredit this null hypothesis and provide evidence to support our alternative hypothesis, but we always start by assuming that the null hypothesis is true. And then we check if our sample data is consistent with this hypothesis. It's really important to note here that with hypothesis testing, we're not trying to prove the alternative hypothesis. For example, we cannot prove that the blood pressure of coffee drinkers is different from the general population. Instead, we try to disprove the null hypothesis that these populations have the same blood pressure. If we can convince ourselves that the null hypothesis is not true, this provides us with evidence that the alternative hypothesis is likely true. So the next step is to make sure that the assumptions for hypothesis testing are met. Last week we discussed the assumptions necessary for the calculation of confidence intervals, and the same assumptions apply for hypothesis testing. The sampled values are independent, so the selection of one participant or observation does not affect the likelihood of selecting another participant or observation. The selection of the sample is obtained through a simple random sample, so participants are obtained randomly. And the third assumption is that the population is normally distributed or our sample size is large, so greater than 20 as a general guideline. And we can usually determine whether or not these criteria are met by reviewing a description of the study design. The third step is to calculate a test statistic. One example of a test statistic is a t-statistic, but we'll also calculate other test statistics as we progress in the course. In general, a test statistic tells us how far our sample statistic is from the hypothesized value for it in terms of the standard error, or the average deviation from the hypothesized value for the statistic. Using the same example as before, Our sample statistic is the mean blood pressure among a sample of coffee drinkers. Since we start by assuming that the null hypothesis is true, our hypothesized value for the mean blood pressure for the sample of coffee drinkers is equal to the mean blood pressure of the general population. So in this case, a test statistic would tell us how far our sample mean blood pressure is from the population mean blood pressure in terms of the average deviation from the population mean blood pressure. But as we discussed in last week's tutorial, the type of test statistic used will depend on what we know about the truth of a population. If the true standard deviation is known, we calculate a z-score. If the true standard deviation is not known and we must use our sample standard deviation as an estimate of this, which is usually the case, we account for this extra uncertainty by using the t-distribution and calculate a t-statistic instead. When we begin discussing other types of hypothesis tests, the process is really similar. In general, most test statistics are calculated by subtracting the hypothesized value for a statistic from the value of our sample statistic and dividing by the standard error of the relevant statistic. So once we've calculated our test statistic, our next step is to calculate the p-value associated with our test statistic. And a p-value is defined as the probability of observing the data given that the assumption is true. And based on our calculated p-value, we then determine if we should reject or fail to reject the null hypothesis. So the p-value is the probability of observing our sample statistic, or a sample statistic more extreme, given that our null hypothesis is true. With our example, this would be the probability of getting the sample mean blood pressure we observed among coffee drinkers, or one more extreme, given that the mean blood pressure of coffee drinkers is actually equal to that of the general population. Another way of saying this is that our p-value tells us that if our null hypothesis is true, how likely are we to get a sample statistic that is as far or further from the hypothesis value in terms of standard errors merely by chance. Based on this p-value, we then decide whether this p-value is small enough to reject our null hypothesis. In order to do this, we must decide which significance level to use for our test. And we denote the significance level by using alpha. If our p-value for our test statistic is less than our alpha, then we reject the null hypothesis and have evidence to believe that the alternative hypothesis is likely true. If our p-value is equal to or greater than our alpha, then we fail to reject the null hypothesis and do not have evidence to believe that the alternative hypothesis is true. The alpha most often used is 0.05. So if we get a p-value less than 0.05, then we can reject our null hypothesis. An important thing to note here is that the p-value is not the probability that the null hypothesis is true. People often make this mistake of interpreting p-values in this way. The p-value is the probability of observing what we did in our sample, or something more extreme, given that our null hypothesis really is true. So, for example, the probability that we would observe the sample mean blood pressure among coffee drinkers, or one more extreme, given that their mean blood pressure is actually the same as the general population. So let's try an example problem. A study was conducted to see if the caloric intake of Vancouverites is different, so either higher or lower, than the recommended 2,000 calories. 800 Vancouverites were randomly and independently sampled, and their average calorie consumption was 1989 with a sample standard deviation of 150. Can the researchers conclude that the mean daily caloric intake is different from 2000? Use a significance level of 5%. What is the null hypothesis, the alternative hypothesis? Are the assumptions met? What is the test statistic? What is the p-value? And do we reject or fail to reject the null hypothesis? So our null hypothesis is that the true mean equals 2000. So Vancouverites eat the recommended 2000 calories per day. And so remember that we start by assuming this to be true and then try to see if we can find evidence against it or in support of our alternative hypothesis. So the alternative hypothesis here is that the true mean does not equal 2000, or that Vancouverites do not eat the recommended 2000 calories per day. They either eat more or less than 2000 calories. Based on the description of the study, we know that our sample values were independent and obtained randomly, and our sample size is 800, so we know that this is large enough for the central limit theorem to apply. Since we don't know the true standard deviation, we calculate a t-statistic as our test statistic, rather than a z-statistic. And we assume that the true mean is 2000, our sample mean is 1989, our standard deviation is 150, and our sample size is 800. So we plug this into our formula to calculate a t-statistic of negative 2.07, and we interpret this as our observed sample mean of 1989 calories is 2.07 standard errors below 2000, our hypothesized true mean value for caloric intake. We then determine our p-value based on our test statistic. Remember that we're doing a two-sided test here because we're interested in determining if the caloric intake of Vancouverites is different, so either higher or lower than 2000 calories. So we can calculate our p-value using software to get a value of 0.038, or we can look at our t-table and see that a t-statistic of negative 2.07 with a two-sided test gives us a p-value between 0.02 and 0.05, or between 2 and 5%. So it's not as accurate as using R or other software, but it still gives us a good approximation. So if we use our p-value that we calculated using software, this would tell us that if we assume that our null hypothesis is true, that a mean caloric intake of 2000 is correct, we would observe a sample mean of 1989, or more extreme, 3.8% of the time. So now our next step is, based on this p-value, do we reject or fail to reject the null hypothesis? And we had said that our significance level, or alpha, is 5%. So since our p-value of 0.038 is lower than our alpha of 0.05, we reject our null hypothesis that the true mean caloric intake is 2000 and conclude that we have evidence to believe that our alternative hypothesis is likely true and that the mean caloric intake for Vancouverites is not 2000 calories per day. Note that we're not concluding that the caloric intake for Vancouverites is 1989, or that we prove that our alternative hypothesis is true, but that we have evidence to support our alternative hypothesis. Sometimes we're interested only in determining if our sample mean is higher than the population mean or lower than the population mean. In this case, we could do a one-sided test rather than a two-sided test. Our alternative hypothesis would be different in this case. For example, it could be that the mean is less than 2000 calories per day. Our assumptions would still be met based on our study design, and our calculation of our t-statistic would also be the same. So it would give us a t-statistic of negative 2.07. We then determine our p-value based on this test statistic. And so to get this p-value for a one-sided test, we are only interested in the probability in the tail of one side of our sampling distribution rather than two sides. So we can use software or a t-table to get our p-value, and we find that this is 0.019, which unsurprisingly equals exactly half of our p-value when we did a two-sided test. Since our p-value is less than 0.05, we reject our null hypothesis and conclude that we have evidence to support our alternative hypothesis. So we can see here that compared to the two-sided test, our p-value is lower here. With the one-sided test, there's only a 1.9% likelihood that Vancouverites actually have a mean caloric intake of 2000, and our observed sample mean of 1989 is due to chance alone. Compare that to the two-sided test, where there was a 3.8% chance that the mean caloric intake was actually 2000, and we observed our sample mean due to chance alone. So with a two-sided test, we need to observe a more extreme difference in our sample compared to the population. So in other words, we need to get a more extreme test statistic to get the same level of confidence as a one-sided test that our results are not simply due to chance. And this is the main reason why scientists agree that we should always conduct two-sided tests rather than one-sided tests. Using a two-sided test is more conservative than a one-sided test because a two-tailed test needs a more extreme test statistic, so stronger evidence, to reject the null hypothesis. This allows you to be more confident that there is in fact a significant difference because it reduces the likelihood of what's known as a type 1 error, which we'll talk about in a minute. And another reason why most scientists think we should always conduct two-sided tests is because if you use only a one-sided test, you're only testing for a significant result in a specific direction. So for example, higher or lower. So if the results happen to be statistically significant, but in the opposite direction than you expected, you would not detect this. So now we're going to discuss the different types of errors we may get when conducting a hypothesis test. So as we've discussed, we draw one of two conclusions from a hypothesis test. We either reject or fail to reject our null hypothesis. But we do not actually know if our conclusion is correct. If we did, there would be no point in doing a test. We draw one of these two conclusions, but this conclusion may be actually false in reality. So this table shows the different situations we can have depending on the conclusion we make about the null hypothesis based on our test, which is shown on the left, and whether or not the null hypothesis is true in reality, which is shown on the top. So we can fail to reject the null hypothesis when the null hypothesis is true in reality, which means we made the correct decision. Or we may reject the null hypothesis when the null hypothesis is false in reality, which is also the correct decision. But there are also two possible errors we can make. A type 1 error occurs when the null hypothesis is true in reality, but by chance we get a sample with a p-value below our alpha level and incorrectly reject the null hypothesis. So we conclude that there is a difference when there actually isn't. So using our previous example, this would be when Vancouverites actually do eat a mean of 2,000 calories per day in reality, but by chance we get a sample that gives us a p-value less than our alpha, and we reject the null hypothesis and falsely conclude that their caloric intake is different than 2,000. The probability of a type 1 error is alpha. So when we choose our significance level, or alpha, we're effectively choosing our type 1 error rate. So if this is 0.05, then the probability that we will reject our null hypothesis when it is actually true is 5%. And a type 1 error is also known as a false positive, which we talked about earlier in the course. A type 2 error occurs when the null hypothesis is false in reality, but we fail to reject it. So we conclude that there isn't a difference when there actually is in reality. So again, using our previous example, this would be the case when Vancouverites actually do not eat 2,000 calories a day. They have a different caloric intake, but our sample mean is not extreme enough to reject our null hypothesis, so we incorrectly fail to reject our null hypothesis. And this is also known as a false negative, and beta is the symbol used to denote a type 2 error. So as we discussed earlier in the course, a false positive or type 1 error is the complement of specificity, and a false negative or type 2 error is the complement of sensitivity. The sensitivity of a test is also referred to as the power of a test. The power of a test is the probability of rejecting the null hypothesis when the null hypothesis is actually false. In other words, the power is the probability of correctly detecting a false null hypothesis. We can also think of power as the likelihood that we will obtain evidence to support our alternative hypothesis when it is actually true in reality. So using our earlier example, this would be the probability that we correctly reject the null hypothesis and conclude that we have evidence to suggest that the mean caloric intake of Vancouverites is different than 2000, when this difference actually exists in reality. So let's try an activity. Think for a moment about a medical test for a severe disease such as HIV. Would you be more accepting of a type 1 or a type 2 error? What about a disease where the tests were invasive and led to potentially harmful treatment? So for this first situation, a type 2 error or false negative would probably be worse, because this would give the patient the dangerous illusion of being HIV negative, and the patient might not get available treatment to prevent disease progression. On the other hand, if you had a type 1 error in this case, or a false positive, this would also be an issue because this would likely cause unnecessary anxiety to the patient. But this would also likely lead to additional testing procedures, and ultimately the patient would most likely discover that the initial test was incorrect. So this is probably better than giving a patient the incorrect assurance that she does not have HIV when she in fact does. So it would probably be better to have a type 1 error in this case. But what about a disease where the tests were invasive and led to potentially harmful treatment? In this case, a false positive or type 1 error would result in a person without the disease going through harmful treatments. So assuming the disease is not life-threatening if left untreated, we would probably be more accepting of a type 2 error or false negative in this case. So now we're going to discuss more details about the relationship between alpha, beta, power, and specificity. And this slide shows how these values are interrelated. So each of the two graphs shows two sampling distributions, one where the null hypothesis is true and one where the alternative hypothesis is true. The top graph shows a situation where our level of significance, or alpha, is quite small. So for example, this could be 0.01 instead of 0.05. The 0.01 p-value means that there is a 1% probability that we will incorrectly reject our null hypothesis or conclude that there is a difference when there actually isn't one. In this situation, we must get quite an extreme value to reject our null hypothesis and conclude that there is a difference of some kind. In this situation, we can see that the power of our test, so beta minus 1, shown in red, is complementary to our type 2 error rate, beta, which is shown in blue. So these add up to 1 in the alternative hypothesis sampling distribution because they're complementary. So compared to the graph on the bottom, the power or sensitivity of our test is lower in this case. So we have a lower probability of finding evidence to support our alternative hypothesis that there is a difference when there actually is a difference in reality. But our type 2 error rate is higher here than the case on the bottom. So we have a greater likelihood of incorrectly failing to reject the null hypothesis with the graph on the top. In language that's a little bit easier to understand, we're more likely to conclude that there is no difference when there actually is a difference in reality. So our false negative rate is higher. And compared to the graph on the bottom, in the graph on the top, our type 1 error rate or false positive rate is lower, meaning that we have a lower likelihood of falsely rejecting the null hypothesis or concluding that there is a difference when there actually isn't. So when we lower our level of significance, say to 0.01 rather than 0.05, for example, this means that we set our critical value to a more extreme value and require a more extreme test statistic to reject our null hypothesis, like what's shown in the top graph here. We have a lower likelihood of a false positive, a type 1 error, and a greater likelihood of a false negative, or type 2 error. The bottom graph shows what happens when we shift our critical value, or our significance level, so that a less extreme value is needed to reject our null hypothesis. Let's say, for example, that we move our alpha to 0.20 rather than 0.05 or 0.01. This means that our likelihood of a type 1 error, so falsely rejecting the null hypothesis, increases. our power, in this case, also increases. We have a greater likelihood of detecting a false null hypothesis and finding evidence to support our alternative hypothesis. But our type 2 error rate, or our likelihood of concluding that there isn't a difference when there actually is in reality, decreases. So the take-home message from all of this is that increasing our alpha, or the likelihood of a type 1 error, is associated with a decrease in the probability of a type 2 error, and vice versa. So that's the trade-off when conducting a study, determining your likelihood of incorrectly stating that there is a difference versus incorrectly stating that there is no difference. Also, as our alpha, or type 1 error rate, increases, our power increases. So if we want to increase our likelihood that we'll detect a difference that actually exists, we also increase the likelihood that we incorrectly state that there is a difference when there actually isn't one. And finally, as power increases, specificity decreases. If we want to increase our likelihood of detecting a difference that actually exists, we decrease our likelihood of concluding that there is no difference when there actually isn't one. So if this isn't sinking in yet, I wouldn't worry too much. It's not the most intuitive, but it'll become more clear as we use more examples. So you might want to try taking a look at these slides again later once we've had a more in-depth discussion about power and tried some examples. But the main thing to understand is that these values are very much interrelated, and that when we determine, for example, our level of significance or our desired power for a test, this will have consequences for these other values. So now let's turn to how we actually calculate the power of a test. Using the sample size equation found in your module notes, you can rearrange the formula to solve for Z beta, which is the Z score corresponding to a probability of a type 2 error. The next step is to look up the corresponding probability for that Z beta in a Z table, and since power equals 1 minus beta, the final step is to subtract beta from 1 to get your power. So we'll try an example in a minute, but usually though, power is fixed at 80%, and we're trying to determine the smallest sample size needed to obtain our desired power. So there are two different formulas for determining sample size, depending on whether you are doing a one-sided or a two-sided test. The only difference in the sample size calculations for a one or two-sided test is the Z alpha, the value of Z with an area of alpha in the tail or tails. So for example, with an alpha or significance level of 5%, the most commonly used alpha, your Z alpha will be 1.645 if you're doing a one-sided test. And if you're doing a two-sided test with an alpha of 5%, your Z alpha will be 1.96. But of course, these values will change depending on your level of significance that you decide on. The Z beta does not change depending on whether you're doing a one or two-sided test. This value will be the same regardless of whether or not you do a one or two-sided test. We'll go through an example, but I would suggest that you try out the examples in Module 3 on page 36, where you can try out different sample size calculations depending on the power level and whether you're conducting a one or two-sided test. So let's try a couple of example problems for sample size and power calculation. Nationally, performance on a mathematics test for fourth graders is reported to be normally distributed with a mean of 40 and a standard deviation of 9. You would like to know whether the average performance of children in your school district differs from the national average. You believe that a difference as small as 3 points is important to detect. How many randomly selected students do you need to include in your sample to have a power of 80% to detect a difference of 3 points using a two-tailed test with a significance level of 0.05? So here's our sample size calculation formula. The first thing we do is look at a Z table to determine the first Z value in our equation, our Z alpha. Since this is a two-sided test with a significance level or alpha of 5%, we're interested in the Z score that would give us 2.5% in each tail. So our first Z value in our formula is 1.96. Our second Z score, Z beta, is the value of Z with an area of beta in the tail. And this is because 1 minus beta equals power. So we subtract our desired power of 0.8 from 1 to get 0.20. So we want a Z score with a corresponding probability of 0.20 in the upper tail. If we look at our Z table, we determine that 0.20 in the upper tail corresponds to a Z of 0.84. Note that in contrast to our first Z score, Z alpha, where we were looking at a Z score that corresponded to having 2.5% in each tail, since we're doing a two-sided test, we do not do the same with our Z beta. We plug these Z scores into our equation, as well as our standard deviation of 9 and our effect size of 3, and this gives us a sample size of 70.56. With sample size calculations, you always round up because you can't have 0.56 of a person, so this gives us 71. The interpretation would then be that 71 students are needed in the sample to detect a difference of 3 points using a two-sided test with a significance level of 0.05. The second question is, your friend collected data from a sample of 25 children from a large school where the mean is 45. If she uses a one-tailed test with an alpha of 0.01, what is the statistical power? So we use our power calculation formula. We plug in our sample size of 25. Our effect size is our sample mean of 45 minus the mean of the population of 40, which equals 5. And our population standard deviation is 9. Our alpha is 2.33 since we're doing a one-sided test with an alpha of 1%. And so we then do the math, and this gives us a Z beta of 0.45. And if we check our Z table, we can see that a Z beta of 0.45 corresponds to a beta or type 2 error rate of 0.326. So this means that the probability of a type 2 error is 32.6%. Since power is 1 minus beta, our final step is to subtract beta from 1, which gives us power of 67.4%. So this means that there's a 67.4% chance that we will correctly reject the null hypothesis when the null hypothesis is not true in reality. So here's another way to determine power for this practice problem. So here's all the information that we know. And so step 1 is, in order to reject the null hypothesis, we need a Z score of what? And remember that we set our alpha level to 1%. Since our alpha is set at 1% and we're doing a one-sided test, we know that with a p-value of 0.01, we'll get a Z of 2.33. So for the next step, we convert this Z score into our study units to get the critical value and find our rejection region. So the rejection region tells us the value we need in units from our study to reject the null hypothesis. So we can simply use our Z score formula to solve for the sample mean that we need to reject the null hypothesis. So our null hypothesis is equivalent to the population mean. Our standard error is the standard deviation divided by the square root of the sample size. So we plug this into our formula to solve for the sample mean needed to reject the null hypothesis, and find that we need a sample mean of 44.19 to reject our null hypothesis. So now that we have our rejection region value, we calculate our Z beta based on our observed difference of 5 that we'll need to calculate power. And remember that power equals 1 minus beta. So now we'll find our beta. Our Z beta pertains to the portion of the curve shown in green here. And this tells us the probability that we will fail to reject the null hypothesis when the alternative hypothesis is true. To find the Z beta, we use the same formula as before. So take a second to think about what value you should use for your expected value. Remember that this is the value pertaining to when we will reject the null hypothesis based on our chosen alpha of 1%. So it's our critical value of 44.19. And our observed is the mean of 45 that we observed in our sample. So our formula is our critical value minus our observed value divided by the standard error. And this gives us a Z beta of negative 0.45. And when you put this into a Z table, like we did before, you get a probability of 0.326. And since power equals 1 minus beta, we subtract our beta from 1 to get 0.674, which means that our power is 67.4%. So as you can see, we got the same power from both methods that we used. You may prefer one method over the other, and that's fine. The main difference is that one way you will know the rejection region, which might be important for the study you're conducting. So please don't worry too much if you don't quite understand this yet, because this is some of the most difficult material in the course, and it takes some time to learn. But one thing I would definitely recommend would be to review the discussion of power in the Pagano text, and I think this is on pages 239 to 249, and I find that pretty helpful. So next week we'll finish up discussing some of the important concepts from modules 3 and 4, and we'll continue our discussion of power. And we'll also talk about tests and plots for examining bivariate data, as well as parametric methods. And finally, we'll conclude with some more practice questions to help you prepare for the midterm.